something is an interesting experience. This gives you more understanding. But if that is a problem, then you can also study an electronic device. And as I told you that there won't be any, uh, don't worry that your marks will be less if you take one kind of project. That's not going to be the case. Your marks will be proportional to the amount of effort that you would be putting in this project. Yes, Ayush.
Hello.
Yeah.
Yes, sir, I was thinking about the nine polar robot or kind of project, and I, sir, I searched through
Okay,
the.
you are not audible. Can you please
Hello,
can you please?
sir, am I audible right now?
Yeah,
So, sir,
your
I
voice
was
is breaking.
hello,
Yeah.
hello. So, sir, I was going through internet about these kind of projects, Arduino related, and I found out like the price would vary from 1 to 2K. So, you asked about the reimbursement process. So, is it possible for the this amount range?
Yes. I will actually let you know the exact figure after I check with the EC office, but around 1500 rupees can be reimbursed. That shouldn't be a problem. So don't worry about that.
Yes,
Okay.
1500 for would do the work. So, would that
Yes,
is that possible?
should be sufficient.
Okay, sir.
Yeah, your voice seems to be breaking. So around 1500 we can reimburse it. If you have uh, arranged something and made something from that, we can do that.
Okay, sir.
Yeah, so Ayush and Dikshant also have raised hands.
Yes, sir. Sir, I am asking that can two students have same project? Like I don't
Yes,
know who is making what, so that's why I'm asking.
yes, definitely. Yeah, so since everybody is at their hometown and you are fairly independent, although it might be possible that some of you might be from the same town and you might um, interact or meet with each other. That's also possible, but I'm not considering that possibility. So two of you can have the same project, but I would recommend you to do independent projects. All of you to independent projects doesn't mean that your projects need to be different. Your projects need can be similar. Don't just make the projects copy of each other. Uh, that is not encouraged. But your broad topics. So, for example, you can two of you or three of you can make a line follower robot. That's allowed. But uh, the methods might differ, or the so everybody will have a unique way of doing stuff.
And sir, one more question. That the reimbursement will depend on the project. Like if you like the project, then that there will be reimbursement or for everyone.
No, don't worry. If you have genuinely bought something from your pockets, so everybody will be reimbursed. Uh, but the thing is that please don't waste it because 100 students and 1500 rupees is a big deal for the department. So I would say just make the purchase judiciously. And so once you all of you decide the project, actually only then I would be able to let you know about the amount that can be reimbursed from the department. So some of you will opt for the study project, studying the electronic device kind of project, and some of you will opt uh, for uh, for this building kind of project. So if the number of students opting for building kind of project is less, then maybe more amount of money can be reimbursed. And if the number of students opting for building project is more, then the less amount of money can be reimbursed.
Yes, sir. And sir, one last, that you said to give us the list of the project which our seniors made and also the sites, online sites where we can buy the components. So please can
Yeah,
you
yeah,
give?
yeah. I told you to do. Yes. So for that, Sanjana and Kunal will share the list with you, at least the projects that they did, and I will see the list of projects. I'll share the list of projects that were done last semester. So we will do that. And uh, uh, Kunal and Sanjana have more experience on building things, so you can directly talk to them about where to buy things from. Okay.
Okay, sir.
So, Kunal, Sanjana, and Jyotish, please share your contact details, including phone numbers, with everybody here, on maybe on the Teams group itself, so that everyone can get in touch with you.
Okay, sir, we'll do that.
Can you please switch on your videos, all the three TAs, so that at least yeah, I hope you can see all three of them. Okay. So, so they are the TAs for this course, but you please consider them to be your like your seniors as well in general. So you can also get in touch with them if you have any kind of questions about the campus, or if you are coming back to the campus, you might be uh, uh, having a lot of things to ask. So I hope all three of you would be available for that kind of discussion as well. Okay, so so that's all. Just if you want to ask anything from the TAs, you can do that. Otherwise, we can start our discussion of the class. And the TAs, if they want, they can leave. Any questions for the TAs? Yeah, if not, then maybe I'll share my screen, and Jyoti, Kunal, and Sanjana, you can leave if you want. And please share your details just after this.
Yeah, I'm making a post on the Teams for that. Sanjana and Kunal can add their info to
Yes. Thank you, all three of you. So let me share the screen. So I hope you can see the slides now. And,
that. Yes, sir.
Yes, sir.
so this is what, yeah. So this is what we have been discussing. This is what we discussed last time as well. This is a quick review of last time. We saw that when a large number of atoms come close to each other, then or when electrons are confined in solids, and solids have a complex interior, I would say. So there is a complex interaction between the electrons and the atoms in the solids, and in that case, bands and band gap are formed, basically. Okay. So if the electron is free, then electron can have any energy. Every energy is allowed for the electron to take. But if electron is confined, then the allowed energies that the electron can take are discretized, as is the case in atoms. But if the electron is in solid, which is a more complex kind of confinement, uh, in that case, bands and band gaps are formed. And depending on how bands and band gaps are arranged, or are there in the material is becomes a metal or a semiconductor or an insulator. Okay, and semiconductors are interesting kind of materials because semiconductors lie between metals and insulator. In metals, we generally have either overlapping bands or we have half filled or partially filled bands. In insulators, the band gaps are pretty huge, so the possibility of electronic conduction is very small. Okay, and in semiconductors, this band gap is in the intermediate range, so the electrons can move from one band to another, from the valence band to the conduction band easily. And there is one more kind of engineering that we can do, especially in semiconductors. This can also be done in insulators, but in insulators, it doesn't make much difference. So this is known as the doping. Doping basically means putting a different atom in the lattice of the semiconductor. So for example, if we put arsenic or antimony in silicon, it has they have 5 electrons in the outermost shell, and but the silicon lattice is arranged in such a way that 4 silicon atoms are connected to each other. So if an arsenic or antimony is put in this lattice, one of the outermost electrons will be free, and that is known as the free electron. That will be free from the bonds with the silicon atom. Okay. So this phenomenon is known as the phenomenon of doping. And similarly, if we put some atom which has only 3 electrons in the outermost shell, in that case there is a vacancy, and that basically contributes as in a hole. And this is how actually this lattice will look like for silicon. In the case when we have put an atom which has more number of electrons, for example, arsenic or antimony, there is an excess of free electrons in the silicon crystal. And that is why this kind of doping or this kind of arrangement is known as the N-type doping. And the silicon or the semiconductor becomes the N-type material. N-type means now negative type carriers are there in more number, they are more free to move around. Similarly, if we have a boron atom placed, it will, and there are, for example, there are 1,000 silicon atoms, and we have put 10 boron atoms. That will make 10 more holes in the system, and the system becomes the holes become more as compared to the free electrons, and these kind of materials are known as the p-type material, because now this hole, which is assumed to be a positively charged particle, they become more in number. So that is the picture, uh, sort of broadly, that is how it looks like in physical world. In energy band diagram, this is how doping looks like. This plot, basically, this figure here. So we have a valence band, we have a conduction band, and when we put a donor atom, which means an atom which has more number of electrons than the semiconductor. In the case of silicon, this can be arsenic or antimony. If we put a donor atom essentially introduces an energy level in the band gap. So now the band structure or the energy level scheme of this material in presence of donor atom is it still has the conduction band electrons, conduction band and valence band, and electrons in valence band and some electrons in conduction band. But in addition to these two bands, there is a small level, there is one or few levels are introduced in the band gap. In the case of pure silicon, there was nothing in the band gap, but in the case of doped silicon, allowed energy levels are introduced. and these energy levels might contain some electrons. So that's why if we have an energy level that is very close to the conduction band and it contains an electron, in that case, the electron that is sitting in this energy level that can easily jump to the conduction band, and that can contribute in the conductivity of the material. And similarly, in the p-type materials, an energy level is introduced very close to the valence band, and the energy level is free. So now the electrons can jump from the valence band to the energy level, creating holes in the valence band. So that's how roughly the uh, the energy level scheme changes when we dope the material with a donor or an acceptor atom. In n-type material, the dopant atom is known as the donor atom, and in p-type material, it is known as the acceptor atom, because now it accepts an electron from the other silicon atoms. So a pure silicon is, and these things are pretty general. I guess you might be aware of these things. A pure semiconductor is known as the intrinsic semiconductor, but the semiconductor that is doped is known as the extrinsic semiconductor. And in extrinsic semiconductors, there can be two type of extrinsic semiconductors. One is the n-type and second is p-type. Okay, and yes, so now basically the currents in extrinsic semiconductors, the currents can be because of the electron flow or it can be because of the hole flow. Okay, so that is a key difference between metals and semiconductors. In metals, the current can only be because of the electron largely. But in semiconductors, the current can be because of electrons or because of holes. Okay, and they behave differently when an external field is applied on the material. So I have a small question for all of you here. Uh, in metals, generally, according to your knowledge, how is the current conducted in metals? What is the picture that you have in your mind?
Sorry, your screen is, I think, not visible.
Yeah, so so I'm not talking about uh, the this
Sir, due to the drift
displayed
speed,
on the
the drift
screen.
velocity.
I'm asking you,
Sir, due to the drift velocity of the
due
electrons,
to the
sir, they vibrate slowly at their positions and the current flows.
So they move in the electric field slowly with a certain drift speed.
they move in the electric field. Okay, but how is it different in semiconductors?
So in semiconductors, they are like moving from one atom to another, and like they are jumping from one atom to another. Like from previous atom, electron came, and the electron from the current atom jumped to next atom from one hole to another. And the
Some
free electrons generated from heat were moving directly.
some metals can be imagined as like a sea of electrons, and when we apply a potential difference, the electrons move in the electric field. Whereas in semiconductors, they are more or less fixed, so electrons move from hole to hole.
And sir, maybe in semiconductors, holes also move. That's
Yes, yeah. So there is one key difference, as many of you have already pointed out. In metals, electrons need not jump from one band to another band. So generally, metals have overlapping bands or partially filled bands. So in that case, electrons. So there is a sea of electrons. There are in almost infinite number of electrons available for conduction and almost infinite number of states, a huge number of states available for conduction. In semiconductors, we need to have we need to make space for conduction in a way, and these dopant atoms, they provide a space For example, they introduce an energy level in the band gap, and this energy level can either take electrons from the valence band and it will create holes in the valence band, so making space for electrons to move in the holes, or it can supply electrons to the conduction band, making electrons available in conduction band for transport. So that is sort of key difference, and that is also a power of semiconductors, because in semiconductors we have two kind of charge carriers, electrons and holes. But in metals we only have electrons. So there can be two type of semiconductors, n-type semiconductor or p-type semiconductor. But metals are generally are abundant in they have abundance of electrons, and we cannot say that there is a p-type metal or n-type metal. And you will see very soon that having different type of material is actually quite advantageous, because the first electronic device that we will study is a semiconductor junction, and that is simply that is formed simply combining the two kind of materials. Nothing great in that. We just put n-type and p-type material very close to each other in a very good way, which means the fabrication is done in a very fine way, and then we have a semiconductor PN junction or a diode, which is a very useful device, which becomes a useful device. So having these two type of polarity of carriers, having two type of semiconducting materials is actually quite advantageous for semiconductors. And there is this final concept in the charge carrier, that is the notion of majority and minority carriers. So if we have an n-type material, in this case, so for example, there are 1,000 silicon atoms in the lattice, and we put 100 arsenic atoms. So 100 electrons will be free from the bonds. So electrons will be in axis, and before putting the arsenic, there might be 10 electrons, 10 holes. But now there would be 10 plus 100 electrons, and holes will be 10 or maybe even less than 10, because some electrons may recombine with the holes. So in this case, the electrons become the majority carriers. So in n-type material, electrons are majority carriers because there are lot of electrons, and holes are minority carriers because there is a very less number of holes. Similarly, in p-type materials, holes are majority carriers because the number of holes is way more than the number of electrons, and electrons are minority carriers because the number of electrons is way less than the number of holes. Okay, so these were some basic things about electrons, and let me sort of quickly also go through these notions. So as I
So
told you in the beginning, we are not going,
have more
yes,
than one extra electrons?
sorry.
So can the donor atom have more than one extra electron?
Yeah, that's a good question. So you are saying that we can put, for example, atom having 6 electrons in the outermost shell, like a sulfur or maybe an oxygen atom. So those kind of dopings have been tested on, especially on silicon atoms, but they do not make a good crystal. The problem is, in that kind of doping, the deformations start happening. It seems that the crystal deformation happens more in a big way. So, so that's why, and crystal deformation actually they produce another kind of barrier. So, for example, if the bonds are distorted, these bonds with silicon atoms are distorted. In that case, the flow of electrons and flow of holes will be interrupted, and it becomes uh, unpredictable kind of system. So we want the donor atom not to disturb the lattice structure, just introduce a single electron. So that is generally has been observed when we dope either with arsenic or antimony or with boron. So that's why these three dopants are generally the most popular ones. Although in principle, the answer to your question is yes. A dopant atom can definitely have two free electrons, or maybe even more than two, three free electrons. But generally, that does not make a very good device because of other problems.
Sir,
Okay. Yeah.
sir, I want to say that if sir, my explanation can be like this, sir. If we add a 6 electron atom in the instead of a silicon atom, then sir, conductivity cannot be controlled that way because more electrons will be present. So sir, it will be somewhat a resemblance to the metal also.
Conductivity cannot be controlled. So you are saying that conductivity will become too much.
Yes, sir. Sir, it will be come close to the metal range. So, sir, we cannot dope with a 6 electron species or a 2 electron species. Sir, two holes or a
Uh,
2 electrons extra.
yeah. So yeah, you are right in principle, but the thing is, nowadays we have very good techniques in which we can control the amount, or we can control the number of dopant atoms. So we can, so if we have a dopant which has 2 electrons free, we can put half of those dopants. Okay, so that's not a problem actually. So
Okay, sir.
that way the total number of electrons will be the same as we put double the number of dopants with one free electron. Okay.
So, sir, in that case, sir, if this happens, sir, like two antimony and one like chlorine or something like that atom. So, sir, in that the crystal will be disturbed. So, sir, that expression will be will take.
Yes, generally it has been actually silicon has been experimented a lot. Silicon is one of the most studied element, I would say, because of its technological applications. And it's true that definitely we can dope silicon with sulfur or oxygen, oxygen or uh, those kind of things. But generally, the doping with arsenic, antimony, and boron, nitrogen in some cases, these kind of dopings are the most sort of optimized ones, which means that they do not disturb the crystal structure too much. They do not change the bond energies, bond angles too much. And it seems that the crystal deformations are also less. So this is what has been sort of finally it has been boiled down to just doping with arsenic, antimony, boron, or nitrogen in some cases.
Okay, sir. Got it.
Okay, so just to summarize some of the things, finally in semiconductors we can have electrons and holes that are available for conduction. And please don't forget that all electronic devices are about controlling the flow of charge carriers, controlling the electrons. So ultimately we want to have a controlled flow of electrons or holes in our semiconductor. But there is a problem actually. So if we and we know that nowadays the transistors are becoming smaller and smaller. So when the transistors are very small, like few nanometers only, which is the case nowadays. So if we have a transistor whose channel length is, let's say, only 4 5 nanometer, it means that it only contains 30 40 atoms in the channel, because one atom is around 1 angstrom or 1 to 4 angstrom generally. So it has only few atoms in the channel. So in some cases, it might happen that when the electron travels in very small devices, modern devices, it may not collide with anything in between. So it may directly go from the one terminal to another terminal, from source terminal to the drain terminal. And that kind of transport is known as the ballistic transport. Ballistic means a bullet-like transport. Generally, the picture that we have in our mind is that electron starts from one end, it collides with somebody in between, it then changes its direction, it may collide with somebody else. Then by this zigzag motion, electron finally reaches to the right contact, right side. So that way the current flows through the materials. But in modern nanoscale devices, this picture is no longer true. Nowadays, we might have a direct electron conduction from the source to the drain side, and that way no collision in between, and that is known as the ballistic transport. Okay, so what I want to say is that the transport, the mechanism of transport is changing fundamentally in modern devices. As the devices are becoming smaller and smaller, as we saw from the slides in our initial classes, that the devices are becoming smaller and smaller because of the high performance. The mechanism of transport is changing a lot. Actually, the physics of transport is changing a lot. So it is an entire course actually on transport theory of electrons in nanoscale devices. This is an entire course that you will have an option to take in your maybe third year or fourth year. And related to this mechanism of transport is the idea of conductivity. So conductivity, the picture that we have in our mind, as I just told you, that the conductivity of a material is ultimately the average of the motion of the electron that takes place in the material after electrons collide with intermediate atoms or other particles. So this idea of conductivity is changing a lot, especially in nanoscale devices. So I just give you a thought experiment. So we have, let's say we have a transistor, and a transistor is a 3-terminal device. Let's say we have a left contact, okay? We have a left contact, a right contact, and in between there is a channel. The channel is very small. The electron is starting from the left contact. It is not colliding with anything in the channel, directly going to the right contact. So this transport is ballistic transport. So now my question to you is, would there be a resistance in this system or not? Because since electron is not colliding, and generally the picture of resistance that we have in mind is that the resistance is because of the collisions in the material. So in ballistic case, would there be a resistance in the device, or it will be a sort of superconductor material?
So there will be.
Yeah, so yeah, please justify your answer as well. So what do you
Sir,
think, why
because
would there be?
yes, sir.
Yeah.
Sir, because colliding is just not the only resistance. There, but I guess is that there are fields of atoms also, and just not by colliding, the electron will get resistance. It will also get resistance due to opposing fields of atoms, nearby atoms, through which it is passing. Sir, you are on
So
mute.
you are saying, yeah, you are saying that it is not just the collisions, it is also the electric fields that is also
Yes.
that contributes in resistance. Okay. Anybody else has anything to add here?
Sir, I don't know if I'm right, but it
Yeah,
will
please.
also have a finite speed, like it will not be instantaneous. So is that also considered in resistance?
No, what do you think? Should it be considered in resistance or no? Even in superconductors, where it seems that the resistance is not there or very small resistance, it is not infinite speed. It is not instantaneous transfer.
Yeah, okay, sir.
Okay. Anybody else has anything to add to it?
Sir, I think an opposite field will be created due to creation of an hole.
Opposite field will be created due to the
creation of holes at one end.
Okay. So
So it that oppose the motion of electron.
No, but we have applied a battery across the device, so that is supplying electrons and in continuously supplying electrons in the system. That shouldn't be a problem, I guess.
Okay.
Yeah, so the interesting thing is that apparently it might seem from our uh, basic idea of transport that a basic idea of resistance, that the resistance might not be there in this case, especially in ballistic transport case, but that is not true actually. The resistance is there, but the resistance is not because of the channel now. The resistance is because of the contacts, because of the Fermi level difference in the Fermi levels. So, so this is I brought this point to highlight the importance of more advanced notions. Let me share the slides again, and the notions of the Fermi level, for example, that you will see in your coming courses, and how that is changing as we are moving towards smaller devices. That is also important. So are you guys aware of direct and indirect semiconductors? Another important concept in semiconductor physics, which is not there in metals and insulator. So we are talking about the distinct points of semiconductors. Are you guys aware of direct and indirect semiconductors?
No, sir. No, sir. I
No,
haven't.
no, sir.
Did did someone
No,
say
sir.
yes?
Sir, I think, sir, indirect semiconductor means something in a combination like GAAS and like that. And direct are like silicon, gallium, and all.
Okay. Yes. Yeah, you are right, but you said it on in the opposite way. Direct semiconductor means the silicon, germanium are indirect bandgap semiconductor, and gallium arsenide, gallium nitride are direct bandgap semiconductor. So there is an interesting idea in semiconductor physics, and that is essentially that comes from the solid state physics. This red line here in these figures, that is the top of the valence band. So we are plotting the energy of electron as a function of momentum. So please remember this, that in while we do quantum mechanical calculations for electrons, the energy momentum relations is very important. So that this relation tells us about how many electrons with certain momentum has what amount of energy in the system. So this energy momentum relation is actually known as the band structure of the semiconductors, and you can see that this red line is the top of the valence band and green line is the bottom of the conduction band. So you can see that there are two types of possibilities. There are two possibilities that the semiconductors can have. One is when the top of the valence band and the bottom of the conduction band are at the same momentum value, at the same K value. Okay. So that is one possibility. And second is when the valence band maxima and the conduction band minima, they happen at different momentum values, different K values basically. And this K comes from the electronic wave function. So the semiconductors in which the valence band maxima and the conduction band minima is at the same momentum value, they are known as the direct bandgap semiconductor. And the semiconductors for which the maxima of valence band and the minima of conduction band are displaced on the momentum axis, they are not at the same momentum value, they are known as the indirect bandgap semiconductor. Is this point clear? If not, please ask questions.
Can you please repeat?
Yes, anybody else has a question? Okay, let me
Sir,
rephrase
why
this.
in like silicon there is a shift and why there is no shift in like the combination of two? The direct one.
Yes. So yeah, first let me rephrase what I said to you. We saw in last slide, in this slide, in the first slide itself, I showed you that there is a valence band, there is a conduction band. Okay. This is the band gap E versus X plot. X axis here is the X axis. So if the semiconductor is this much long, this is how the energy is separated, and this gap is there. So electrons cannot take any value in this range, any energy value in this range, right? This point is understood.
Yes, sir.
Now, what I'm
Yes, sir.
saying is that if we plot E versus K, that was E versus X, E versus K, which means we are plotting the allowed energy values as a function of momentum of electrons. K value. So momentum, if you remember the wave equation, any wave equation generally has a K value. So for example, psi can, a wave function of the electron can be A sine kx. So K is the wave number or momentum of the wave number, or it represents the momentum. So if we plot, instead of plotting E versus X, we plot E versus K. In that case, we see that now this is the way the bands can be.
So
Sorry,
you
you
are
are on
mute.
mute.
Yeah, so what I'm saying is that if we plot E versus K, in that case, it might happen that, so in this case also there is a gap. There is a range of energy values that the electrons cannot take, this gap or this gap. But now it might happen that this maxima of the valence band and the minima of the conduction band, they might be aligned with each other. They might be at the same K value, or they might be at the different K values. Okay. When they are at the same K value, the semiconductor is known as the direct band gap semiconductor. And when they are at the different K values, the semiconductor is known as the indirect band gap semiconductor. Now, is this clear? Please, if not, please ask. I can repeat again.
Sir, it's clear.
Yeah, so now next question that you will ask is, and somebody I guess has already asked this, why does this happen in some cases? So for example, why is silicon like that and gallium arsenide? Why is silicon indirect and gallium arsenide direct? Okay, that is purely, comes from the, that is purely a consequence of the structure of the silicon crystal. So silicon crystal has a different crystalline structure, and gallium arsenide has different crystalline structure. So that's why the potential energy of electrons in silicon is different than the potential energy of the electrons in gallium arsenide. And if we solve the Schrodinger equation for silicon potential energy, we get this kind of solution, indirect band gap solution. And if we solve the Schrodinger equation for gallium arsenide, this kind of solutions are obtained. So that is purely a consequence of the quantum mechanical nature of electrons. Okay, that is there, that is how it is actually. But now, how are these two kind of semiconductors different from each other? I guess that is more important question. How is a direct band gap semiconductor different than the indirect band gap semiconductor? In the direct band gap semiconductor, if there is an electron sitting in the valence band, and if it gets good amount of energy, it can directly jump to the conduction band if it gets sufficient energy. So for example, if we strike a photon on this semiconductor and the electron absorbs the photon, it absorbs the energy, it may jump to the conduction band. But in this case, electron, if we supply this much energy, this arrow amount of energy equal to this height of arrow, this electron sitting at the top of the valence band, if this gets this energy, it will still be in the band gap. So it needs to change the momentum in order to reach to the bottom of the conduction band. Got it or not?
Yes,
In
sir.
the indirect band gap semiconductor, if the electrons generally, whenever there is a transition of electrons from valence band to conduction band, generally the electrons at the top of the valence band, they go to the bottom of the conduction band. And in indirect band gap semiconductor, if the electrons here, they need to go to the bottom of the conduction band, they need to change the momentum as well. So which means that in addition to energy, we also need to supply some momentum, or we also need to change the momentum of electrons in indirect band gap semiconductors. Okay.
Sir, I have a question. Sir, in
Yes,
indirect band gap, can we give more energy to transfer the electron to conduction band instead of
you are
giving
right.
the momentum?
Yes, so we can definitely give high energy and the electron will go here maybe. But then if there is a state that is empty below this state, so now let's say the electron was initially here, it can go to this energy level, but conduction band has an energy state which is empty below this level. So all these states are empty, right? So now electron will change the momentum to occupy the lowest energy state. That is the thermodynamics at room temperature. And how does it happen? It happens via phonon collisions with phonons. And what are phonons? Phonons are essentially the vibrations of the crystal. So as all of us know that at room temperature or at any finite temperature, all the atoms are vibrating slightly. So there are slight vibrations in the atoms, and electrons may be electrons may be kicked because of these vibrations. Electrons, because of the vibrations, the interaction of the electron with the atoms change, and that way the electrons can change their momentum. So as you said, if the electron takes higher energy, it will go here, but because of the phonons, because of the vibrations, it will adjust its momentum such that it occupies the lowest energy. It will eventually come to the bottom of the conduction band. All right.
Okay, sir.
So, however, in direct semiconductors, that is not the case. In direct semiconductors, they can just absorb minimal energy, the energy difference between the bottom of the conduction band to the top of the valence band, this amount of energy if they absorb, they can make the transition.
Sir,
Yes.
sir, in indirect one, sir, the momentum
Yeah.
change will always be like that. They always go to the least energy point of conduction band.
Yes, so that is governed by the thermodynamics actually. If electron is sitting in higher energy state and there are energy states below this level, empty energy states below this level, electron will eventually come back to the lowest available energy state. Okay. So eventually electron will interact with the vibrating atoms in such a way that it will ultimately occupy the lowest available energy state. So that is the thermodynamics ultimately.
Okay.
On the
I
contrary, yes.
want to clarify that you said when in the indirect band, the electron jumps from one atom valence band to the other atom's conduction band. That's why this is happening.
No, it is in the same. So first of all, the valence band and conduction band do not belong to individual atoms. Okay, the valence band, conduction band are for the entire solid. Individual atoms have energy levels, discrete energy levels. Here we are talking about the entire solid. So now in this solid entire semiconductor, there is a conduction band, there is a valence band. In direct band gap semiconductors, the conduction band minima and valence band maxima are aligned. They are at the same momentum. In In direct bandgap semiconductor, they are misaligned. So which means that if an electron needs to make a transition from the top of the valence band to the bottom of the conduction band, it needs to change momentum as well, in addition to energy. Okay, is this
I'm
point?
not getting why they are not aligned in the indirect one.
Yeah, so why they are not aligned is a consequence of their basic physics. It comes from the solution of the Schrodinger equation. So if we do the analysis of electronic energy in solids, different solids will have different EK plots. EK means energy versus momentum plots. Okay.
Okay.
And that is a consequence of their basic physics. That is because of their basic interactions, because each solid has different kind of interactions in this, different number of atoms, different kind of arrangements. So they will have different kind of EK relationships. So some of them obtain this kind of EK relationship, the so-called direct band gap kind of relationship, and some of them obtain this indirect band gap kind of relationship. Okay. Now, on the contrary, let me quickly finish this topic. Now, let's say, so as you might have seen here, that at room temperature, always there are some electrons in this picture. There are some electrons that are sitting in the conduction band, and some states at the top of the valence band are empty. So now let's say this is the situation in both kind of semiconductors. So there are some electrons here and some states here are empty. Similarly, some electrons are sitting here and some states here are empty. Now, we can, in direct bandgap semiconductor, we can have, if you are aware of this term, stimulated emission. If we strike a photon, the photon can cause the electron to go down. I am presuming that you guys are aware of the theory of lasers. Okay, so in that case, the electron here in the direct bandgap semiconductor, it can absorb or it can directly go to the valence band and it might emit a photon.
Sir, I don't know the theory of lasers.
Okay, so without even knowing the theory of lasers, uh, let's say the electron is sitting here at the bottom of the conduction band. Okay, and if it makes a transition from here to the top of the valence band, this energy difference will be emitted can be emitted in terms of photons. So this excess energy will be emitted in photons. In this case, however, if the electron sitting here, bottom of the conduction band, and it has some states empty at the top of the valence band, it cannot come here because these states are all occupied. Most of the valence band are occupied. Only some states at the top are empty. So if this electron here at the bottom of the conduction band, it needs to come to the top of the valence band, it needs to change the momentum, which means it needs to interact with the vibrations. It needs to collide with the atoms. And that way, in this case, the energy is dissipated in collisions. In this case, energy may come out in photons, in terms of photons. In indirect bandgap semiconductors, most of the energy in electronic transition is dissipated in phonons. Is this point more or less clear or not? This is an important point actually. I mean, from the application point of view, this is important.
Sir, in second case, the energy released is used for collision.
Yes, so in the second case, electron is here, it needs to come to this level. So it needs to change the momentum, and in order to change the momentum, it needs to collide with the phonons. So with phonons, so electron may lose energy to the phonons, most of the energy to the phonons. So its momentum will be changed and its energy will also be lost. In this case, however, the electron does not need any phonon. It can emit energy in photons as well.
Okay, sir.
And that is precisely the reason that the LEDs or the light emitting diodes or lasers, any device that needs emission of light, that is made of the direct band gap semiconductors. And that's an important idea actually in semiconductor device applications, that silicon, which is among the most popular semiconductor, but it is indirect band gap semiconductor. And because of that fact, we cannot make LEDs out of silicon, because during the electronic transition, silicon does not emit photons. It emits very less number of photons. It mostly its energy is the electronic energy is dissipated in phonons. Okay, so the LEDs or lasers are made out of direct band gap semiconductors, and for transistor operation, we don't need to worry about the direct band gap or indirect band gap transition band gap semiconductor, because in that case we do not need transitions from one band to another band. In these optical applications, in the LED and laser applications, I'll tell you the the basic functioning of an LED as well, semiconductor LED. Okay, and that then it will become more clear. But please remember this thing, that direct bandgap semiconductors are used mostly in optical applications. So there is a question from Devanshu. How is energy increased without any change in momentum? So yes, so energy can be increased. We can increase maybe the potential energy just of the system. Okay, so that way the velocity magnitude may not change, the direction may not change, but the potential energy of the system will increase, and that way the total energy will increase. So we are bringing the electron from the bottom to the top, from the top of the valence band to the bottom of the conduction band. I hope this is clear, and there is a next question by Mayank. You said, you said phonons are vibrations. Then how electrons can collide with vibrations? Yeah. This will become clear to you maybe in your physics course, that these lattice vibrations, they are modeled by quasi particles. They are not actual particles. Uh, they behave like particles, because even the energy of the vibrations is quantized like the energy of photons, and that's why they are known as the phonons. And when electrons are attracted or electrons are impacted by the vibrations, for example, if a lattice is vibrating like this, atom is vibrating, it will collide with electron, or it may change the direction of the electron, or it may change the energy of the electron. The energy transfer between the vibrating atom and the electron also happens in quantas. Okay, so this interaction is also pretty much similar to the interaction of electrons with the photons, and that's why I told, or I mentioned, that electrons are colliding with vibrations, because in a way electrons are colliding with phonons, but that is not physically what is happening. Physically, uh, vibrations vibrating atoms will collide with the electrons, not the phonons. Phonons is just a mathematical idea.
So you said silicon is an indirect semiconductor.
Indirect.
So is it just an example or the logic behind it?
No, I told you that this is an example, definitely an example, and the logic behind is that uh, that each element or each solid has different EK relationship, and that EK relationship is because of the atom because of the crystalline structure of that semiconductor, because of the how many electrons are there in the outermost shell, how those electrons are interacting with the atomic shells. Okay, so those kind of interactions ultimately determine the EK relationship of the entire solid. And in silicon, it turns out to be that that it becomes an indirect band gap semiconductor.
So, sir, it's not like that the elemental semiconductors will be the indirect one and the compound semiconductors will be the direct one. It's not like that.
No, no, it cannot be generalized in this way.
Okay, sir.
Generally, however, generally it has been observed that these 3-5 semiconductors, 3-5 means element belonging to group 3 and group 5, when they come together, gallium arsenide, gallium nitride, those are direct band gap semiconductors. But there are some semiconductors, 2-6 semiconductors as well, and they may be or may not be direct band gap semiconductors. So it is not the case that elemental semiconductors are indirect and compound semiconductors are direct. Okay.
Okay, sir.
Yeah, so that is the idea of direct and indirect band gap semiconductors. That is also one of the important topics in the semiconductor physics. Then I guess today we don't have time, but the next topic that we will briefly study is the Hall effect experiment. This is an important experiment in solid states, and you will do this experiment in your second year in the lab here as well. Okay, and we'll discuss this in the next class, and then we will start with the discussion
Sir,
of
basically
the
this question
yeah.
came in JEE Advanced some paper some time back. Sir, this question, the Hall effect.
Yes, what was the question about? What was the
Sir, it
question?
was something about the magnetic field and the electrons deviation, and we have to calculate some relation about voltage and all.
Exactly.
So
So
it was taught
that's a,
to us in the lectures on.
yeah, it might have been taught to you, and and this is not a difficult calculation, I would say. Okay, so
Yes, sir.
we'll discuss that in the coming class. It's a straightforward experiment, but it has some interesting consequences. We can deduce some important ideas from the Hall effect experiment. This experiment is very simple in principle, but the consequences are very important. There is one more question from Kartikeya. Can the bottom of conduction band in indirect semiconductor be on the left side of the momentum correspond? Yes, definitely it can be on the left side. They just have to be misaligned with each other. Okay.
So how can we join the WhatsApp group from TAs?
Yes. So your entire batch will be divided in 3 groups, and I will share the joining links of each groups with your CR. So CR will forward it to you. I'll also send the group links on email, and then you can join the groups. Okay.
So can you please share the contact details of the TAs?
Yes, the TAs might themselves have done that. I told them to do that. So if you go to the Teams page of the course, you can see the details of Jyotishwaran, Sanjana, and Kunal, all 3 of them. Email and phone numbers. Okay. So feel free to talk to them about any question regarding the course project, the course, or in general as well. Okay, so let's close the class for the day, and thank you
Thank you, sir.
for joining. Yes, see you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah, bye.
Thanks, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.